All right. So, welcome everyone to New Energy Updates Icing Mitigation webinar for wind executives. We are doing this in partnership with Engie Canada and Nergica. This is Diana Dropo, and I will be your webinar host for this morning. Now, before we start, I'll tell you a few words about New Energy Update and the purpose of this webinar for those of you who haven't probably heard of us before. In short, New Energy Update is an organization that helps decision makers anticipate the renewable energy future and hopefully formulates what is cost-effective plans in the face of constant change in this industry. And generally, we figure out how to do this through independent market research and international conferences and so on and so forth. In Wind O&M specifically, we deliver webinars, reports, white papers, and so we will be looking to provide you with valuable content that you can hopefully use to stay ahead of the changes and developments that will have a direct impact on your performance and production. So now, this webinar will focus on how to best deal with cold climate challenges and anti-icing technologies. One note to take into account is that we're always looking for collaborators, so feel free to reach out to me after the webinar if you're interested to start a conversation. Before we kick start, I want to point out why we are all here. So put simply, wind operators are investing a lot of money in tools to mitigate cold weather issues, such as icing on rotor blades, and which is the #1 cause of wind turbine downtime in cold climates. So this is why it's really important to know how to create a strategy to evaluate different anti-icing solutions and develop a business case that will prove your return on investment at the end of the day. So we are really excited to partner with Mark Hatchie from Engie Canada and Charles Gaudreau from Nergica to give you some practical advice on icing mitigation. In short, Mark will help you understand the operational takeaways related to cold weather mitigation for Canadian owner-operators. After that, Charles will talk about the technologies that you should be looking to adopt to minimize production loss due to icing and to recover lost revenue. And finally, both our speakers will share some thoughts on delivering a good icing mitigation strategy with a focus on planning and investment and applicability. So yeah, exciting stuff. Remember that you can always send your questions at any time for our Q&A. And if you have any technical problems, just drop me, the organizer, a message directly. And before you all ask, the recordings for this webinar will be emailed to you in case you can't stay for the entire session. Yeah, thank you all in advance. I hope you enjoy it. We're going to be running a poll just before Mark will kickstart with his presentation. So watch your screens and reply to the questions that will help us understand more about you, our audience, to deliver a valuable result. Thank you very much, guys. So we are now sharing the results for the first question. You can have a look at your screen and understand a little bit more about everybody who's joining this webinar today. It looks like it's a majority of wind farm operators. We are launching the second question of the poll that has to do with your regions. It's important for us to understand where most of you are based. So we're now sharing the results that will show where most of you are based. You can see the percentages on the screen. And we've now moved to the last question that has to do with icing issues. We want to understand how often you deal with these issues, if you deal with them at all. And now you can see the results for the last question of the poll. All right, thank you very much. Thank you for responding to our poll questions. I am going to hand you now to Mark. Mark, please take us away.
All right. Just going to share my screen here. I'm just waiting so I can get my split screen is not working right now. There we go. All right, so I'm assuming, Diana, I'm coming through. All right, so I'd like to thank New Energy Update for the opportunity to share some of my experiences. Some positives, some negative. Hopefully, there'll be people out there that can complement what I'm saying, and maybe in the long run we can all help each other. So, as she had mentioned, my name is Mark Hache. I am the manager, excuse me, at Caribou Wind Park. We're a 99 megawatt wind park. We have Vestas V90, 3 megawatt turbines, and we are located in Eastern Canada, as you can see on the screen here. We are located on the east coast of Canada at an elevation of around 850 meters, around 2,800 feet. It's a mountainous area. The mountains aren't super high, but they are the highest mountains in Eastern Canada. And unfortunately, as it so happens, though, we are kind of in the middle of the jet stream. So the clouds that people see in town is the fog that we have passing through our site. So this is where a lot of the icing tends to be problematic for us. So I'll go through some of my experiences so that you people won't have to either go through them yourselves, or you can take away to hopefully continue where I left off. So I have a few pictures here on the next slide showing you some of the issues we have. In the winter, there's really 3 issues, right? We have equipment damage, we have production issues, and we have safety issues. On the pictures here, the equipment damage issues really are the top left and right. We have numerous issues in the past where we had excessive ice accumulation on the overhead collector lines. You can see the sag there. We had significant damage, which we've since fixed by beefing up the collector lines, adding poles, guy wires, etc. On the right-hand side, you can see another impact here. We had our substation fence. It collected a lot of ice and fell over, so we obviously had to repair that as well. So just examples. On the bottom left You can see some blade damage. That's ice impact damage. Numerous times we have to repair blade ice damage on the blades. Bottom right, this is the safety aspect where we have falling ice. You can see the stairs where the ice has fallen and damaged the stairs. In the middle, prime example of blade ice. This is a pretty bad case where there's ice really on the whole turbine, including the tower. So I'll go to the next slide here. Now talking a little bit about the safety aspect. Some of the reasons why we aren't able to get turbines running really is safety related, which means there might be a simple problem with the turbine. We're unable to get in the turbine because of the risk of falling ice. So we've invented, well, I say invented, but we've designed and constructed, we call it a portable ice roof, that we're able to pull it, it's on skis, to the turbine where the wind technicians are able to get into the turbine safely to do whatever they need to do to get the turbine back in operation when the turbines don't have so much ice that they're not able, that they are still able to run, but they're just not able to get into the turbine safely. The bottom right is another unit that we built. It's a second version of it. It's lighter, a little easier to use. So we have it positioned here just to show you how it looks when the people enter the turbine. So we found we probably lose 40 to 50% in some years lost production just because of safety related issues, not so much aerodynamic issues on the turbine itself. So these are some of the trials that we did with blade icing. The first thing that we had tried a few years back was a surface mounted heating tiles, electrically, obviously electric heated tiles where they're stuck on the surface and they're interconnected electrically in between the tiles. This system didn't really work well for us. It only worked a couple times. Unfortunately, it wasn't physically reliable, nor was it electrically reliable. The electrical issues we had, the biggest one really was the interconnecting. I'm not sure if you can see my mouse on the screen, but where the gentleman in the yellowish green shirt, each heating tile is interconnected electrically, and those connections were made too tight. So what happened was when the blade flexes, those connections were pulled apart, causing open circuit, and in some cases we actually had some sparking and some blackening of the blade where there was some sparks. Other issues we had were just the reliability of those tiles. The adhesive wasn't strong enough. You can see on the left picture where some of the tiles simply just fell off after a while. Some of the other tiles, there was a sort of a Kevlar cloth to protect the carbon heating section of it, but with the wind and snow and ice and rain, those coverings wore off, exposing the inside. So this project really didn't go anywhere. But next thing we tried was painting a set of blades black, just for the fun of it, I guess, to see what it would do for us. So there were some concerns that we had to watch out for here. The biggest concern was overheating. Vestas was concerned, and that's the manufacturer of the turbine. They were concerned that if the blades got too hot, it could soften some of the glue and fiberglass components, causing damage to the blade. So on the right-hand picture, you can see where they wanted us to stay away from the leading and the trailing edges, where the blades were actually where they're bound together with the adhesive. So as you can see, we did that. On the left, you can see an example of we did a ground testing to see what the temperature increase would have been. So we've put different colors. You can see black and gray, lighter gray, and some of the browns as you go away from the picture. And we have little temperature stickies down there, so we could actually measure the temperature increase based on the color that we used. So we determined that the dark black was good. The other colors didn't increase enough, and the dark black wasn't so much that we were concerned too much about overheating the surface of the blade. It's doubtful how well this worked. It seemed that turbines would come, this turbine came online maybe a little sooner in some springs, maybe not. It was really kind of hit and miss. It was difficult to say for certain that there was any impact. Certainly didn't work in the middle of the winter. It was too cold, not enough sun. So we didn't pursue this anymore. We didn't see enough benefit, if any, um, to go any further with this project. Something else we tried a couple of different types of coatings. The first coating, I don't have any pictures here for some reason I couldn't find any, but the first one was an off-the-shelf product. And I won't mention any names for the sake of either saying anything negative or positive. I'll just stay neutral just on the general experience. So the off-the-shelf product, the component or the solution was installed up tower. And we installed it, I would say, I think around October-ish. We had the product tested actually at a Nergica facility in Canada, where they were able to simulate real world impact, such as how quickly the product would wear down because of friction, and also the UV impact from the sun. So they were able to accelerate the aging of the product as well as running through some tests. And they had found that after 3, 4, 5 icing events, the product significantly dropped off in effectiveness. And that's kind of what we found. Actually, was even less than that. The product worked a little bit the first icing event. It really did nothing after that. So what we figure is that just the wind and the ice, and the water and some snow before we got to winter was enough to wear the product down. So by the time we got winter, there really wasn't much product left to do a whole lot. Second product we tried was our new product from Japan. This particular company is a business partner with us, so they have a division in the chemical, so they brought a product here. We applied it. Very complicated process. We had to take the blades down. We had to maintain certain temperature, air pressure, humidity in the tent on the ground. It had to cure at 50 degrees Celsius, so we had to get IR heaters. Very, very complicated process. It didn't work either. We're not quite sure if it was just because of the product itself, or we suspect maybe it was in the application because of the complicated nature of the application. That might have been the problem right from the start, but we can't say for sure. So for me, the takeaway of these is really big questions are, what are the temperatures do you have to apply the product? What's the method? Is it roller? Is it spray? Do you have to prime before you put the product? Do you have to sand the blade? Whenever you have to sand the blade, there's a red flag there. You don't want to damage your blades on a trial, depending on how much of the surface they have to remove. And of course, there's health risks too. The second product was highly toxic. So we really had to be careful with that. You don't want to hurt any of your people just, for these efforts. All right, next slide here. Something else we tried was helicopter spray. And I'll go quickly through, so I'm running out of time here. So the helicopter, it worked a little bit, but it was very slow. We tried it even with the glycol. It worked better, but the biggest issue really was the opportunity to fly with the helicopter. They can only fly within certain wind speeds. If there's snow or rain, he can't fly because of visibility. In the winter, the days are short, so you have less time. Plus, a helicopter, unless you own one, the hourly rate is fairly expensive. So we decided this wasn't a cost-effective option. Next thing we tried was the Vestas heated air system. It worked in the limited icing that we received. However, you'd have to buy 99 new blades for 33 turbines. The cost, there was no economic benefit to doing this product, even though that the technology was useful, was productive. The cost was too much to justify it. We had a government project to measure ice and to determine the icing conditions. We had some issues with the government when they changed party. They dropped the program. However, the biggest takeaway for me really is we use this website here, and we can predict, looking at the humidity, the precipitation, when we're going to get ice in the temperature, when we're going to get an icing event. So we can choose to manually pause turbines during the event, or we can keep them running when we think the event is going to be short, and we can ride it through. So this really has I think, done a lot for us. Seems simple, but it was a very useful tool. Okay, I'm getting near the end here. So in the future, we're looking at another surface-mounted electric heating system. potentially. We're also looking at a ground-based ice removal system. I can't talk about the technology because we're in a non-disclosure agreement, but that will be ready for us to try early next winter. And we're also looking at installing fixed roofs on each turbine instead of hauling around the protection roof. And my last slide, conclusions, there's still hope. A lot of people are working out there on this. Know the site early. Don't build a wind park where you're going to get a lot of ice if you're not able to handle it. And of course, be safe. Don't take any chances when you're trying to remove the ice. So that's what I have. Thank you.
Excellent. Thank you very much, Mark. That was really, really interesting. And for the public, just so you guys know, we are actually collecting your questions, and there will be a section dedicated to Q&A. We will be discussing these once Charles has also finalized his presentation. So stay with us. And right now, I'm going to hand you over to Charles. Here we go.
Thank you, Deanna. Hi, everyone. This is Charles Gaudreau. I'm a project manager, research and innovation at Nergica. I'm based out of Gaspé, Eastern Quebec. And today I'll present to you technologies you should adopt to minimize production loss due to icing and how to recover lost revenue. Maybe briefly, just an introduction of our organization. Nergica is a college-based research center. And so we work in renewable energy research and innovation, mostly in wind, PV, and integration of renewables in remote grids. And so today we'll go over a quick overview of the cold climate in North America, how the icing process is building up on a wind farm, and what technologies are used to address different, let's say, sections of this process. And then we'll look at different technologies available, ice maps, forecasts, detection, mitigation systems. And as Mark was mentioning, some key aspect of health and safety to be aware of when you're operating a wind farm in cold climate. And then we'll look at the icing business case, how you should look at it, build it up, and follow up with technology providers to help you mitigate these issues. So briefly, what is cold climate? So there's, let's say, two climates that overlap in cold climate. That would be the low temperature climate, which is defined by temperatures below -20 Celsius over 9 days in a year, or an average air temperature below 0. And in some cases that overlaps with icing climate, which is either instrumental icing for more than 1% of the year, or meteorological icing during more than 0.5% of the year. A lot of the content I'll be showing today is from the IEA Wind Task 19, which is an expert group composed of 11 countries, and Nergica is the Canadian representative on that group. So low temperature climate, you can see this. This is from Vaisatlas from VTT Research Center in Finland, and they've run simulation over the whole globe, but this is showing cold climate regions in North America, and where you can see that basically most of Canada is low temperature climate, and some of the northern state as well in the Midwest. Then looking at icing climate, here in green, you have low risk, so that would be class 1, in yellow, class 2, and in red, class 3. And basically, you can see that Caribou, the wind farm we're looking at, is in New Brunswick here, and we're based in Gaspé. So in Canada, Eastern Canada is exposed to more icing. At the time they did this simulation, they lacked data for a fair part of the western side of North America. So some, let's say, higher definition icing maps could be useful if you're looking into siting a project. Now the icing process, this is again from Task 19, but basically as an icing event comes into a wind farm, you'll have what we call meteorological icing. That would be when there's an active meteorological phenomenon, could be fog or precipitation that is affecting your wind farm. And then what will happen during that time is there will be a phase of incubation, and then accretion will be the moment where ice is building up, and we'll distinguish between instrumental icing, that is when your wind sensors or icing detectors will detect icing, and rotor icing, which is when the wind turbine blades are covered by ice. And instrumental icing or rotor icing will persist in time, and so that might be that after a meteorological icing event, which lasts, let's say, a day, you could have icing on the wind farm for several weeks, depending on your climate. And so the importance of detecting these events and being aware that there's icing on the wind farm is important, especially for health and safety issues. And looking at that, basically there's kind of three families of technologies you can look at to tackle the icing. There's forecasts. So forecasts, you can have models or maps that will let you know in advance if will be looking into an icing event. Then there's detection, that you can put dedicated sensor on your site so that you're aware that you have icing. And then there's mitigation, where you'll want to be able to remove that rotor icing at some point. And so available technologies, we'll look at ice maps, forecast detection, ice prevention system. Mark has already presented a few of them. There's basically two main families that would be the active system, so hot air, electrothermal, and de-icing fluids. And there's passive system, which are ice-phobic coatings or wind turbine control, and also a few points on health and safety. And most of the content I'll be showing today is covered in the IEA Wind Task 19 Available Technologies report. And as I mentioned earlier, this is an expert group composed of 11 countries, most of them in Europe. There's also China in there, and us from Canada. Also, this Available Technologies report will be updated, and so you should expect a new version to come out later this year or early 2019. So ice maps. Ice maps, I would say, are mostly useful for turbine siting and project development. And so nowadays, several companies offer ways to either do what we call meteorological reanalysis. So that would be to look into historical forecast data and kind of compute how much icing events you'll observe at a given site. And so the image we see here is from Sweden. It was done by Scheller Vindtechnik from Norway. And they are a member of Task 19, and they have basically a method to calculate the occurrence of icing on a site. And on page 5 earlier, we had the one from Weissatlas by VTT. So there are several ways to know in advance, in the development stage, if you have icing and if you need to assess it in your basically project evaluation. Another useful thing is Icing Forecast. Most of them are provided for free by national forecast agencies. In Canada, we have the GEMLAM model from Environment Canada, and in the US, they have the WRF model. And this is a picture from the National Center for Atmospheric Research in Colorado, running the WRF model, I believe. And since icing is also an issue in aerospace, if you look into airport data and or FAA regulations, you'll have several details on the forecasts available and the frequency where you can look at them. I would say that if you're operating a wind farm in cold climate, you should have a look at a proper icing forecast, at least 2 times a day. It's just a best practice to be aware of, what are the conditions coming to your site, and if you need to implement some mitigation. Maybe also note that there's commercial solutions available. So some companies will be able to provide you, let's say, adjusted forecast for a given site. And so you might be looking into that as well. Now, icing detection, there's several ways to detect icing on your site. There are what we call indirect methods, which are basically measuring icing through another measurement. And so there's double anemometry, which is comparing a heated versus unheated cup anemometer. Based on our experience, and we've published on that, you want your heated sensor to be ultrasonic. Some of the heated cup anemometers don't have enough power to basically melt the ice, and so they'll have faulty readings in icing. And you also have a heated bearing on your unheated cup anemometer, because in low temperature, you'll be getting false alarms. So be aware that non-heated bearings will, cup anemometer will slow down in low temperature. And so the ideal pair would be heated ultrasonic with heated bearing unheated cup anemometer. Another method that works well is power curve degradation. So once you have icing on the blades, the turbine will produce less power. The thing with that is once the turbine is stopped, then you can't say if there's icing. So you want to be able to have an alternative method if your turbine is stopped. And then another method that was used in the past was looking at atmospheric conditions. So that would be temperature below 2 degrees Celsius and relative humidity above 90%. And our expert group, Task 19, does not recommend using this method. The reason is that basically in low temperature, relative humidity sensors are not working properly. And so that is that below -15, relative humidity on a standard sensor will not even reach 90%. And so you should be aware that if you're using this to look into some more precise methods of detections. Now there's a lot of direct methods available now. In the past, it used to be, let's say, a lot of new products on the market. I think now there is, let's say, established ice detectors available. One of them is LabCotec. MCMS is Meteorological Condition Monitoring Station. It's from Canada. There's the Goodrich, supplied by Campbell Scientific, PMS Ice Meter, Linolin, New Avionics, Holo-Optics. So there's a few options out there. And then there's rotor-based sensor. So there's Eologics, Phosphorex, Vermueller, and Wolfeld. These works by either measuring the load on the blades, so that they know that they have an increased load on the blade, which is caused by icing, or by directly detecting icing on the blade, which is what Eologics do. And on that topic, we've been conducting a performance analysis comparisons between Eologics, Phosphorex, and Vermueller. And so if you're interested in looking at these results, please get in touch with me. We'll have a report available soon. And what we've developed at Nergica to kind of validate these and look into ice protection system performance is cameras. So we have two different types of cameras, which are nacelle or hub-based. And this is basically what we do with our camera, is that we have the nacelle camera looking at a reference tube, and from it we can pull out automated results, which gives severity, so that is how much ice you have in the on the nacelle, the rate at which it builds up, and the duration of the event. And so these can be quite useful for us to be able to validate if a sensor is working properly or not, and if the turbine was under the effect of icing at a given time. And then we have the hub camera, which is, you see it here, it's proprietary from Nergica. Basically, it's a heated stainless steel ice shield. We have a full HD camera and an infrared illuminator for night vision. It's fully remote and it's compliant with electrical safety codes. And this is an example of the view we can get from that camera, looking at the blade. And if the turbine is equipped with a de-icing system, we can evaluate if the de-icing cycle is effective. So these are two cameras that we use in, well, let's say technology evaluation projects. Now, ice mitigation systems is also, there's quite a lot of solutions out there. Basically, all the major OEMs now offer an icing mitigation or de-icing system, some kind of de-icing system. So you've got Dongfang, Enercon, GE, Senvion, and Vestas working with the hot air. And on electrothermal, you got Dongfang, Nordex, Siemens Gamesa. Vestas has just released a new electrothermal de-icing system. And Vicetech, which is a technology provider from Finland. Now, as Mark showed previously, if you've done your site assessment properly, that you know that you have some icing issues, and that you bought an OEM de-icing system, that's fine. I guess the main trouble is you've built up your wind farm when either this technology was not available or not knowing that you would get so much icing. And so I guess that the retrofit system is something that operators in icing climates have been looking for a while. And it used to be that, as Mark mentioned, it would be some kind of new system that hasn't been tried before with some reliability issues. And I guess that some of them have kind of worked around this. So there are a few out there. There's Borealis Wind, which is a new company from Canada. They're doing a retrofit hot air de-icing system. There are some considerations in your blade design. If your blades have, let's say, closed sections, then it might be a bit more complex to install. But it's basically just a, let's say, flexible duct that is introduced into the blade, and that will push hot air to the leading edge. We've seen some results at our conference past June, and it seems to work well. There's Spitzer Engineering from Germany. They supply similar to what Mark shown, kind of heating elements that you would stick to the blade. And there's Vicetech Ice Prevention System, which is based on a conductive carbon fiber. The retrofit of that system is a bit more complex. You need to bring down the blade, but the conductive element is then applied into the blade structure. So you need to remove the gel coat and first layer of fiber, and then you apply this carbon fiber, and all the connections are inside the blade, so there's less, let's say, connectivity issues. We've evaluated this system. Presentations from Winter Wind Conference from last year are available on that project, so if you want more info on that, please get in touch. Some other mitigation systems
Charles,
yeah.
Sorry, it's Diana. Sorry to interrupt. We will have to start with the Q&A because we're running out of time, and we have a lot of questions that we are receiving. I guess that is a good thing after all. But just so that the audience knows, so all the material that we are discussing right now will be distributed to you guys the ones who have signed up and are listening to us now. So that includes both of these presentations and the audio recording. So I think it's best for us to move to a few questions now. We will try to select a few right now. It won't be all of them, but then the speakers, Mark and Charles, will be able to reply to the questions that you're sending through the platform individually to everybody who has sent something through. So I'm going to start now with one question for Mark. Somebody has sent this over. What blade ice mitigation advancements would you like to see in the future?
All right, so I guess without picking on any specific technology, I'd like to see the option of having, especially for sites that are halfway in their contract or later, they're not interested in spending a whole lot of money up front. So any technology where you can call in a contractor that can come in on an as needed basis, remove the ice, and then leave. So you pay per ice removal, as opposed to spending millions of dollars after the fact on a new blade heating technology. Because I mean, that's fine for a young park. We have lots of time to make your money back. But as you get older, the payback is not there. So you really need something quick and easy on an as needed. That's what I'd like to see, whatever that technology might be.
Excellent. Thank you very much. Thank you, Mark. Charles, the next question that I'm going to be putting forward is for you. So how do you tackle icing in project development stage versus the operational stage?
Yeah, that's a good question. So development stage, you want to be able to measure icing. So if you expect that your project is an icing climate, you can have a look at, let's say, ice maps. For instance, ice maps are a good indicator just to know if you'll be facing any icing at all. And then you should also look into a proper site assessment. On that topic, Task 19 has been working with the IEC to provide new guidelines for site assessment in icing climate. And that would be on how to measure icing at a site. So sometimes these, let's say, met masts that are put up at a new project site, they're not fit for icing measurement. And what happens is, oftentimes what we saw, let's say in Quebec, for instance, is that icing data was basically just rejected because they had only unheated cup anemometers, couldn't tell whether it was from icing or from another issue. And so some of the data was just removed. And you should be confident in the icing detection method you choose in the icing assessment. And then once you know how much icing you're looking at, then you can kind of look into the different technologies that you can implement in your site. One thing to comment also is that in Eastern Canada, most of the icing is basically strongly correlated to altitude. So it's in-cloud icing. And so at a given site, if you have a lot of variation in altitude, some of the turbines might require, let's say, electrothermal de-icing system, whereas the lower turbines, they might not even suffer so much icing. So that's something to consider as well. And in operation, yeah, I'm sorry, guys, I didn't have time to complete, but I would say some of the recommendations I had at the end of the slide were to some of the things, if you're in operation and you're not doing this, then it's, a must do is implement forecast for your team on site, and also implement cold climate working procedures. And so there's a reference in my presentation on a best practice guide from Canuya, and I suggest to have a look at that and implement these as fast as you can. And depending on your project age, then you can look into some retrofit systems or just review the project budget. If your co-owners are expecting that you'll only have 2% icing losses and you're suffering 6%, then you'll never be able to reach their goals. So have a look at your icing losses and try to kind of be more precise on your budget forecasts.
Thank you very much, Charles. I have a question for Mark coming up now. How do you decide when to perform ice removal on a specific wind turbine? So basically, which problem is more acute? Is it early detection of icing or the process of removal of icing from the blades? And when do you make this decision?
I'm not sure if I understand the question. So when do you make the decision to remove the ice?
So what is the process that you would have to go through in order to assess when to perform ice removal on a specific wind turbine? How do you assess this on a specific wind turbine?
Well, I mean, if it's whether or not deciding to get a system, I mean, you'd have to know obviously how much downtime, how much you're losing to determine if the technology, if you know the cost benefit is there. I mean, once the system is on, if it's a passive system, it's always going to be working for you. If it's an active system, you know, like an electric type system, then you know it's either a system that runs when it detects ice, so it doesn't remove ice, it prevents it from building to begin with, so it's more of a preventative system. Another system would be like the VESA system that we had tried. You have to stop the turbine after you get ice and then run it, so that it's an after effect thing. So in this case, when the icing's done, you pause the turbine and then you remove the ice that's been built up during the event. So there's different things to consider. I'm still not exactly sure what the question was asking, but hopefully, you know, in one of these situations, it's addressing that question.
Yeah, and if I can comment on that, for basically all the OEMs system, they'll have their own automatic triggering. So it's integrated into SCADA. They'll have some kind of icing detection, either on the nacelle or through power curve degradation, which will either trigger the de-icing system if it's able to run while in operation. There are some design limitations, especially about the power you can pass through the slip ring. And so some systems, since they can't operate the de-icing system at the same time as the pitch motors, they'll shut down the turbine and basically run the de-icing cycle and restart. But this is most of the time all automated. So you don't have necessarily to kind of assess whether or not you should de-ice at that time.
Perfect. Thank you, both of you. I have another quick question for you, Charles. What kind of performance can be expected from ice-phobic coatings?
Yeah. So ice-phobic coatings, one thing to understand is how they work. So ice-phobic coating is basically not, let's say, the right word. So you might expect that you won't have ice buildup, but that's not actually what happens. So these coatings, what they do is they reduce the adhesion force between the ice and the coated surface. And you basically need the same thing as an uncoated blade for the ice to be removed. That is some vibrations, gravity, or some kind of sunshine to kind of help melt the ice. And what we've seen in past evaluation of these technology is, since it reduces the adhesion force of the ice, the more ice you have, the better chances of the coating to work. And so that is when you have a very severe ice buildup, it will fall down from the coated turbine earlier than from an uncoated turbine. But there's some sense of an act of God to it. Could be that there was some kind of gust at the time that helped, you know, shed the ice. We can't really say, but it's not as effective as an active system. And I guess that the durability of these coatings is also something to that needs to be proven. So you can't expect a good performance over a couple of winters maybe, but more than that, you'll have to reapply the product to make sure that you get the same performance.
Wonderful. Thank you very much. Thank you to everybody who got involved. We actually have to wrap up because time has run out now. So thank you all, and especially Engie and Nergica for making this webinar a huge success. We've had more of 400 of you actually around the world join us live, so I hope you've gained even more than what you hope from our expert speaker lineup. Please note before you all ask, because I don't know when everybody joined, the recordings will be sent via email, and so will the presentations, and hopefully we will be able to engage with your questions. We have received them, we have been allocating them on the platform. So the speakers have been receiving them. Unfortunately, the time is short, but we will be heading somewhere from here. What we know from this webinar is that there is a lot of innovation to tackle icing and cold weather problems in general within the wind operator market. And certain technologies and operating models could potentially be a valuable tool to minimize lost production and to help you recover the lost revenue that this has generated. So we will keep covering the most relevant stories for you at New Energy Update. You can always subscribe to our newsletter on our website, and we are always open for collaboration in future webinars and white papers and reports. So if you feel like you're one of those people that would like to collaborate with us, you can contact me directly on the details on the screen. My email is diana@newenergyupdate. You probably receive my emails every week. Until then, though, thank you very much for joining us, everybody, and I hope you all have a beautiful day. Thank you.